something like what we call absence. The formula phi does not hold. This is the kind of idea. Every time the formula phi does not hold, it means globally phi does not hold. Before psi, well, if psi holds at some point, then before phi should not hold. So if psi holds at all, then we talk about this psi, and up to this moment phi should not hold. Or after psi, so psi is some kind of special, identifies a certain position in our work. And how can we express that phi should not hold after psi? Well, this is given by globally. It's the case that once psi holds, then from this point on, phi should never hold. If psi does not become true, everything is fine. Same here. So that's also a way we discussed yesterday a little bit what is different in salt. Salt is one kind of way to have a more abstract language. What we see very often in practical specifications are these kind of scopes. You say, well, there is some dedicated point, and up to this moment something should hold, or starting from this something should hold. If you have a question.
For the last one.
For the last one.
Yeah, I don't know is G not right. No. So what is the idea? So you're interested in the positions where psi holds, and from that on, phi should hold. Okay. So the G means once after psi is holds.
So
not this one, but
we could write F here.
Yeah.
If we write F, then we talk about some position. But we want to talk about, what do we want to talk about?
The first position.
We want to have a first position. So for all positions where psi holds, phi should no longer hold. And that we can express with globally. If we would use finally, or this eventually, then it's not necessarily the first psi that we're considering. We could consider some other psi. So you could have psi words, psi holds here, and from that on, phi doesn't hold.
Yeah, but why isn't it when if psi holds, then phi does not hold everyone even before?
Well, then we would have to express something like before. We will only consider a future fragment. So, it's one of the biggest, the big problems using LPL. So we might have a position in, so this is our work. And maybe psi holds here. And maybe psi holds here as well. So what do we want to express? So what we said, after psi means that we're looking for the first occurrence of psi, and from that on phi should not hold. So what we want that, of course, not phi should hold here, not phi should not hold here, phi should not hold here, and so on, but not starting from this type, but from that one. So we could also try to identify the first position. So if psi, we could try to identify that by saying psi does not hold until psi holds, and then from that on something else holds. Yeah, but we get this implicitly by writing this globally for all positions. Yeah.
For the right part, G of no phi, could you write no non f of phi?
I think not eventually.
That means that phi does not hold in the future. So we can write that because, so in general we have that G phi is equivalent to mod F mod phi, meaning G mod phi is equivalent to mod measure. So phi holds globally. It is not the case that at some position phi does not hold. So globally phi does not hold. It is not the case that phi holds at some position. So these
So now what I did not really understand was that the second G in fact starts in the position where psi holds.
that starts, yeah.
That's what I did not understand.
I see. So you see, it's a little bit tricky. So here we talk about absence, but the pattern change if we talk about existence. The formula phi holds in the future. So if we talk about the whole word, then phi should hold at some point. Okay, obvious. It should hold before psi. So if psi never holds, then that's fine. But in the other case, phi should hold, and up to this moment, psi should not hold. And also, when phi becomes true, psi should not hold. So, at some point, phi should hold before psi becomes true. If psi never becomes true, everything is fine. But if psi becomes true at some point, we want to see phi before. So we want to see phi before psi becomes true. And also when phi becomes true, we don't want to see psi. So we identify. Yeah.
We will also seek out the last occurrence, right?
But then
Instead of the first, we would be able to select the last one.
yes.
Okay. So if the last one, then there is no more.
So
okay.
So phi could be true here and here. The only thing is, before psi becomes true, phi has to be true at least at one point. Or phi has to hold at some point after psi became true. And if psi doesn't become true, that's fine. But if psi becomes true at some point, then at some point later, phi has to become true. Here we say phi can also become true at the same time when psi becomes true. If we want to have it strictly later, then we would write the next f if we universality. So we had absence, we had existence, we had universality. Phi should always hold. If we talk about the whole word, we just write globally phi. Before psi, at some point phi may become true, and then phi has to hold until this moment of psi. And so we want to have phi being true up to the moment psi becomes true. If psi becomes true at all. If phi becomes true, then from that point on phi should hold globally. So whenever psi becomes true, we check globally phi for all positions, meaning we start practically using first position. Yeah. You see that if you look at practical examples, it's a little bit it could be a little bit tricky to write down the right specification.
Yeah.
Okay, so bunch of standard equivalences. So when are two formulas equivalent? Well, two formulas are both equivalent. Phi is equivalent to psi if for all words
every word satisfies phi in the same way as it satisfies psi, like in the usual sense. And from the formal definition, you could derive eventually phi is equivalent to true until phi. Phi has to become true at some point, meaning it has to become true at some point, and up to this moment, nothing special has to hold. True has to hold. True always holds trivial. And you can check that globally phi means false releases phi. False release phi, how do we read it? Phi has to hold all the time up to the moment when this guy becomes true, meaning when false becomes true, false never becomes true, since false is false, so phi has to hold globally. And when we have the typical De Morgan laws in LTL, as you know from propositional logic, the negation of phi of psi is the negation of phi, and the negation of psi, and the dual rule as well. And we have a bunch of equivalences for the temporal operators. And that's the, well, you can understand the release from an intuitive point of view. We can also work easily with the release by just understanding that's the dual of the until. So not phi until psi is equivalent to not phi releases of psi. And vice versa. We have G of phi negated is the same as F mod phi. I mentioned that already on the board. And we have a nice duality also for the next operators. It's not the case that phi holds in the next position if in the next position phi does not hold. And well, the only interesting case is what happens if there is no next position. So here might be two reasons why phi does not hold, if phi does not hold in the next position, or there is no next position. And if there is no next position, then it's fine with a weak operator. And for runtime verification, extremely important are these fixed point equivalencies, as we call them. So phi until psi, what does it mean? Well, there has to be some point where psi holds, and up to this moment phi holds. But you can also understand it in a local fashion, meaning that, so what can happen for the first position? Well, either psi is true, then you're fine. Or psi is not true, so it has to hold later on. But then at least, to be able to continue in the first position, phi has to hold. So, phi until psi is true, if psi is true in the current position, then everything is fine. Or if you didn't meet this goal, then you can continue and try to prove phi until psi starting from the next position, provided that phi holds in the current position. And the release is dual. And it's a dual operator anyway, so how do we get it? We swap or at end and or next to with next until to release. And if we use these unwinding laws for the until and the release, we can also make special proofs for the globally and the finally operators. So globally phi holds if phi holds in the current position, and we continue in the next position proving globally phi. If we are at the end of the word, everything is fine. We have checked phi in every position, so that's good. And dually for the finally phi, well, either phi holds in the current position, or, well, if we didn't manage to prove phi right now, we continue in the next position for the same proof. And that's also the idea of many monitoring procedures. You change the formula, and you check the condition, check a part of the formula in the current position, or you continue. If you don't hit the goal, continue in the next position with the same formula. If you look carefully at all these equations, all these equivalences, you can see that you can push the negation inwards. Here you have the negation of the complicated formula, and you push negation inwards. And Here for the temporal operators you do the same. And so you can push an arbitrary LDL formula into what we call negation normal form. Yeah. So now let's build a monitor for FLTL. So what does it mean? We want to build a function, some kind of device, some kind of automaton as it turns out in the end. Well, first it's more like some kind of program code. It takes an LDL formula into negation normal form, and it takes the word that we have observed. So we're in the setting that the program has terminated. We have a finite run, and we want to check whether this word satisfies our formula phi. And how do we do it? Well, we perform according to the recursive structure, recursive nature of our property phi. And it returns true if our word satisfies our property. Otherwise, it returns false. Well, how can we do that? So if our formula is true or false, everything is clear. True is true, false is false. If we consider phi of psi, well, phi of psi is true by the given word w if phi is true or psi is true. So we can perform recursion both of phi and psi, and then we return the truth values. Then my battery is and so if we have some kind of recursive procedure, we can handle or we can handle and in the same way. If we have an atomic proposition, that's also easy. So we check whether it's satisfied in the first word or not. What about the next operators? So in general, next phi we want to verify. So what do? We just chop out the first letter of the word and check phi on the remaining part. We have to check next phi for the whole word. We have to check phi from the next position on. So chop out the first letter and then check it on the remaining part, whether W2 is. And but we have to check whether the word is empty or not. So we have to have at least 2 letters. What about until and release? Well, until and release are completely easy. Because we said, okay, we can evaluate conjunction, disjunction, negation, atomic propositions, Boolean constants, true and false, for the given word looking at the first position. Now, what do we do for until? Well, we know that phi until psi is equivalent to psi or phi and next something. So we just, whenever we hit an until, we call our procedure recursively with this unwinding. So here's no until that we have to hit. Here we have psi, we have an or, we have an and, we have an next, and we know how to handle that. And whenever we hit the until again, we do the unwinding again. And sooner or later, we are at the end of our word. So that's the full procedure. We call it eval FLTL. And we call it with the word W and our formula. If it is true, everything is fine. We return top. If false, we return bottom. The disjunction, we do the recursive call of phi and psi and return the disjunction of the 2 truth values conjunctionally. For the atomic propositions, we check them in the first position. For the until operator, well, we hit phi until psi, we call it with this unwinding of the until purely for the release. Same for eventually and globally. We check phi or start from the next position, eventually phi purely for globally. And the interesting stuff to terminate the procedure or to complete the procedure are the next formulas. Well, if we have at least some letters left,
then we continue from the second letter on, checking phi. Got a strong bond. And here, if there's nothing more than the current position, everything is fine. Or we check W2, we check phi starting from the second position. Okay, so that's a simple recursive procedure. It terminates, as we can see. Yeah, it's not completely obvious, but it's obvious. So we do a recursive call according to the structure of our formulas. Yes.
Why it terminates? Because the strings are fine, right?
Apparently.
Because the strings we are checking everything are fine.
Yes.
And if it's fine, so eventually I will terminate because every time I'm calling this recursive definition, I'm moving.
Yes.
Yeah, and
exactly. Yeah. Of course, for infinite words, it would not be finite. And the argument is not completely trivial because we do a recursive call on the structure of the formulas, so we increase the size of the formulas. But here we increase it again. So it's not just having a monotonicity argument on the second component won't work. We have to have a combined argument. But yeah, here we extend it, but we add this next, and here we chop off the letters on the first one. Yeah.
However, complexity is still is complete, or
no, I mean that's linear in the size of the word. So it's something like a product in the size of the word and the length of the product.
so it's not like the infinite case.
No, it's not like an infinite case. But we're solving the word problem. We have a given word. So if you would consider that, or if you would compare with the LTL model checking, then from the formula you get an exponentially bigger automaton. But the word problem itself would also be easy with the, more or less easy with the bigger. If you have, let's say, if the infinite word is given as a lasso, then you can also check easily whether it's accepted or not. All right, so that's more or less trivial case. And now we go a little bit into more interesting parts, and we want to do a monitoring procedure for impartial runtime verification. So, what's the goal of the next chapter is we want to understand what impartiality means, and we want to produce, we first give a formal semantics or a logic that is impartial, and it's a full-valued variant of FL. And then we also built the monitoring procedure. Okay. Guess I have 10 seconds. Okay, and then we want to compare the monitoring, or we will build a new monitoring procedure for FLTL4. So, we talked about truth domains, we cover with the full-valued semantics for LTL, the monitoring function corresponding to that semantics, and then we talk about Wheeler machines. So what are the truth domains? The setting that we consider here is different. In the previous chapter we said we have a finite word that is given because the program has terminated. Now we observe the system while it is evolving. So we have our system and we've seen something, and if we went long we see more and more steps. And we want to come up with some result that is fine for what we have seen so far. But yeah, here on the slides. But it's also preliminary regarding what can happen in the future. So let's see. We have two atomic propositions, P and Q, and we consider the properties globally P and globally Q. This one also has a laser pointer, right? Yeah. Changing to that one.
So, what is phi? Phi is globally P. So we want to have that P holds all the time. So let's look at this word. P holds here, P holds here. So W satisfies phi, W satisfies phi here as well. Right? So we're tempted, if you would use the FLT of semantics, we would say true. But if we continue observing the system and we see Q here, then P is not satisfied in this position, so the final result will be false. So we say true, true, false. And yeah, you might say this is okay, but you might also say this is not nice because it's like when you have a student and the student says, I know the answer, and I know the answer, and finally you prove. So if the student would say immediately, I'm not sure about the answer, it would be much better than finally you disprove that you knew the answer. Okay, and of course we have the dual situation here as well. For example, if we consider phi prime that says, at some point I want to see a P, then okay, we haven't seen it in the first position, we would say false. And then we haven't seen it, we would say false. But then suddenly we see the P and we go from false to true. And whatever we see here, we state as true. So there are two things to observe here. We say true, and later on we say something else. And that's in general not nice. The other thing here is this false is a stable false. We have disproven our formula, and whatever happens, we state it's false here. Because we said in all positions P should hold. And we have position 3, this one, where P does not hold. And this false will stay forever. This true changed into false. And then this false stays forever. So in some sense, this false is a real false, and this true is a real true. Similarly here, or dually here, this false is not a real false. Later on it turned into a true. And this true stays true forever, whatever comes in the future, because we wanted to see P, and we have seen P here. So whatever happens, this stays true. So in some sense, this is a real true, and that one is a real false. And this is a cheating true, and this is a cheating false. Meaning, we should distinguish these situations. And that's why we want to have 4 truth values. Here we want to say, well, it doesn't look bad. It's potentially true. And here we say, oh, it's false. Here we say, well, it doesn't look good, but maybe it becomes better in the future, so we can go for potentially false, but here we go for really true. So, impartial means if you go for true or false, you should only do that when you really know, and then you should stick to your word. And impartiality, it's the formal definition, I think we don't have. So, if we consider a logic having no longer 2 truth values, but 4 truth values, or 1 and 2, then we cannot give the semantics in terms of a relation anymore. We give semantics in terms of a function. So in the sequel, we will introduce semantic functions that give us a truth value for some truth domain. We'll study several ones. That give us for a certain word and an RTL from the corresponding value. And the notation that we use is, well, for 2-value logics, we wrote something like W satisfies phi. And what we do here instead, we write these brackets around it to denote that it's a function. Rather than writing a comma, we stick with writing this model sign. It's more like a 2-value function. And it gives us this truth value. So what's the idea that we have
have, well, no, we can use the same stuff for FLTL as well. You can say the two-valued semantics for where W and formula phi is true if W satisfies phi and false. So it's a conservative extension. And what does now impartiality mean in a formal way? Impartiality means that if a word with respect to formula is true, if the word satisfies phi for sure, then whatever we extend, whatever we see in the future, it should stick to true. And if we decide for false, then whatever comes in the future, we should stick to false. And of course, we need multiple values to do that. We cannot do that with two truth values. It's kind of clear because in the beginning we would have to know already what happens in the future. So every two-valued logic is not impartial. So we have to come up with nice domains, and that is for expressing what we understand by truth in a many-valued setting. And the tool that we need for that are lattices. Maybe we take 3-4 minutes and we go through it, and then we have the break. So what is a lattice? It's a partially ordered set, where for any two elements I have a greatest lower bound and I have a least upper bound. I have the mean of two elements. I have an element here and an element there, and then I have the greatest lower bound, the mean. And I have the join of the two elements. Join of two elements, this one. You can think of sets. For sets, the mean could be the intersection and the join could be the union. For two values in the Boolean setting, the mean would be the AND, and the join would be the OR. We are interested in finite lattices. Call lattice finite if the underlying set is finite. So, and in every finite lattice, we have a least element and we have a greatest element. And if you take the mean of all finite elements, then we get the least element, we call it bottom, you know, the sign. And if you take the join of all finite elements, we get the greatest element, and we call it top. And the idea is that bottom means false, top means true, and then we have many truth values in between in our setting. Two. So what are typical examples? Typically we write truth domains using the so-called Hasse diagram. So we write down the elements on the two-dimensional space, and bottom is smaller than top. And these are examples of lattices, not necessarily of truth domains, but of lattices. So P2, we have two elements, true and false. And P2 times 2, we have 4 elements ordered in this way. So you can easily think of this bottom, true, and this is 0, 0, 1, 1, 1, 0, 0, 1. And then the beat and the join could be the intersection of the beats. And you can form Boolean lattices in this way just by adding copies of P2 all the time. Yeah, so here we have a lattice with many elements. Different examples would be these. P2, P3. That's a lattice that we will work with tomorrow. So we have true, false, and don't know.
This is a lattice we might work with today. We have true, false, and maybe true, and maybe false. We want to work with distributive lattices because we want to assign, or we want to give formulas and semantics, and usually we want to have a distribution for our formulas. So the distributive lattice, so the lattices that we're considering should be distributive as well. What is distribution? X and Y or Z is equivalent to X and Y or X and Z. Or X meet Y join Z. It's the same thing that we are used with two-value lattices that translates very well to these lattices. What is important is negation in logics. So the dual of true is false, the dual of false is true. And we want to negate formulas, and we want to give semantics to negation in the way that if this formula evaluates to something, and now we negate the formula, we just have to negate the corresponding truth value. So we need something like negation in or duality in our lattice. And we call the lattice the Morgan lattice if every element has a unique dual element, which has two properties. If we complement twice, we come back to the very same element. A set complemented and complemented again is the very same set. True becomes, the negation of true becomes false, and if we negate again, it becomes true again. And when you think about it, it's also kind of clear the order changes. True is fine, false is bad. If you negate, the order turns around. And I also want to recall the notion of a Boolean lattice. What is a Boolean lattice? If we take a set and join it with its complement, then we get the complete set. That's what we know from power set lattices. So if we take an element and join it with its dual, we get the top element, and if we meet it with its dual element, we got the bottom element. So, and what is the truth domain? The truth domain is a finite De Morgan lattice. We want to have complementation for the elements, duality for the elements, and we want to have distributive lattices. I mentioned it here. Follows. And the typical one that we know is this P2. P3 is another one. P4 is also another one. It's a small exercise before we go into the break, where we have true, false, and don't know. Well, if you complement false, we come to true. If you complement true, we come to false. What is the dual of don't know? It's written there. It's written there, yeah. Okay, reading. So that's good. I thought you were too tired to read. Okay, then you know the same stuff here, right? Right, true, false, possibly true, possibly false. These are the dual lattices. There is a question where we split that. We do it after the break. So now we know what truth domains are, and the goal is now to give a full valued semantics to it. And that we do after the break.
Yeah.
The reordering stuff applies, but it says only if.
No.